Okay, so we are on to the next section. Again, another sort of combination of sections. And this is all about trigonometric functions. Very fancy sounding name. But actually, we already started doing this last time. Last time, we learned about sine of theta and cosine of theta. And so what these are the y and the x value for the point on the unit circle that touches that angle. So that was the idea there. And then what we did is we figured out sine and cosine for some nice angles, like all the pi over 4s, all the pi over 3s, all the pi over 6s, all the pi's, all the pi over 2s. Those are the kinds we got to be able to calculate. But in fact, we could do more rotations too. So before we continue, let's just think about like one more kind of example. So like what is something like this? Sine of 17 pi over 3. So we're looking for a y value that sort of looks like a pi over 3y value. But the trick to this one is first find 17 pi over 3. And I want to emphasize that this can be done quickly. So you shouldn't take very long to do it. And how do you do it quickly? You do this trick where we cut the top and the bottom into thirds. So in this case, 1, 2, 3 on the top, and 1, 2, 3 on the bottom. And then very quickly, I can find 17 pi over 3 by just counting around. So this is 1 pi over 3. This is 2 pi over 3. And that's kind of slow to do it like this. 3 pi over 3, 4 pi over 3. These are the first ones. But 17 pi over 3, that just means keep going. Because this is 6, which is the same as 2 pi over 3, or sorry, which is the same as 2 pi, you can keep going. So this next one, 1 pi over 3, is also the same as 7 pi over 3. And so I need to get all the way to 17. I can go very quickly. I can say 7, 8, 9, 10, 11, 12. And so this will be 13, 14 pi over 3, 15, 16, and finally, here is 17 pi over 3. So the idea is I basically went around once, twice, and then that is 17 pi over 3 rotations. So then what is the answer? Well, what's the coordinate? It is, because it's a pi over 3, it's 1/2 comma root 3 over 2. So that means that this one is the same, except it's going down. So the y value is negative root 3 over 2. So that is the answer, negative root 3 over 2. So we can do that kind of thing. We can also go backwards. We can rotate backwards, meaning we can ask questions like, what is cosine of negative 25 pi over 4? Something like that. And then we can tackle it the same way, but we just have to rotate backwards because we're looking for a negative rotation. So I still just cut the top into that many slices. So it's 4 slices. So 1, 2, 3. That's going to be 4 pi over 4s, 5, 6, 7, 8. And then to get to 25, I can do this pretty quickly because I can do something like this. If I go down, that's negative 1 pi over 4, then negative 2 pi over 4, and so on. But I'll just skip because I already know if I go all the way around, that'll get me to 8 pi over 4, negative because I'm going that way. So then I go around again, that'll take me to negative 16 pi over 4. And then I'll go around a third time. I just have to go multiples of 8 is the trick. So negative 24 pi over 4. That's what happens when I go 3 times around. So then I just have to go, that's negative 24. So now I just have to go one more to get to negative 25 pi over 4. And now I'm at the angle I want. So I'm asking, what is this point here? Well, it's the same as this point up here, except you might have to worry about a negative. So it still goes to the right, so that x is still positive, but you go down, so that's negative. But because it's cosine, I'm looking for the x value there, and so there's your answer. It is root 2 over 2. Okay. So that's how to tackle more rotations. But the next thing we want to do is sort of break away from the unit circle. So there we learned how to rotate more and rotate backwards. But next, what about other circles? So sine and cosine right now are attached to the unit circle. But what if I have a circle that doesn't have radius 1 necessarily? Instead, I don't know, so I'll just call it R. So circle with radius R. Then I want to know, can I still figure out this x and this y based on the angle that I rotate around? So now the radius is R, so instead of this side being 1, it's also R. And I can say a few things, like I can say like this point is R comma 0 for sure. And this is like 0 comma R and so on like that. But I still want to know if I could do what I did before, but now not the unit circle. So I want to sort of figure out this x and this y. Let me erase this R here because that means the whole thing. So can I do that? Can I figure out this x and this y? How are they related to the x and the y for the unit circle, aka sine and cosine of the angle? Because what's going on is like the unit circle is like some smaller circle here, maybe with radius 1. And get this smaller triangle there. And sine of that angle is the height of that littler red triangle. And cosine is the base of that littler red triangle. So how is that related to the x and the y of the blue triangle? Okay, so let's see that. So let's zoom out. So here, let me use the same colors actually. So here's this y and this x, and this thing is r. This angle is theta. This is a right triangle. And then we have the unit circle triangle, where what are these side lengths? Well, they are defined to be sine of the angle is the height, right? Because sine is the height of the triangle you get when you go out by 1 at that angle, because it was defined to be the y coordinate of that triangle. And then this guy, same idea as cosine. And then because they have the same angles, that tells us, if you remember from very, very long ago in like geometry class, that the triangles are called similar. That's not how you spell that though. Similar triangles. And that means that their ratios are the same. These have the same ratios. So they like grow the same. They're proportional to each other. So what that means is that if I look at corresponding sides divided by each other, that they're equivalent. So for example, I can say that sine divided by 1, that ratio is the same as y divided by r. So I can say sine of theta divided by 1 is this y coordinate divided by r. AKA, anything divided by 1, that just doesn't change it. Sine of theta is actually y over r. So this is where people get very confused because they think, well, before you told me sine of theta was just y, and now you're telling me sine of theta is y over r. But those are two different situations. This is for any circle. But if you're specifically on the unit circle, it's just y. But that's not a contradiction, because the unit circle, what's the radius of the unit circle? That's r equals 1 anyway. So that's the same thing, because if I just plug r equals 1 here, then I'll just get this situation back. Okay, so there's no contradiction between saying sine of an angle is the y, the height divided by the radius, versus saying sine of an angle is just the height, because this is specifically only for the unit circle. Okay. And then in a similar way, we can look at the ratios of cosine on this triangle. Oops, why did I put an x in there? That should have been a theta a long time ago. Sorry. Cosine divided by this 1 is equal to x divided by this r. So same idea. Cosine, the ratio of cosine to 1 is the same as the ratio of x to r. So cosine of theta is actually the x coordinate divided by the radius for any circle. And specifically, if the radius happens to be 1, that means you're on the unit circle. So there's no contradiction there either. Okay. So sometimes what people do, so let me recompile this information down here. So people often just say sine is y over r, cosine is x over r, where you're in this situation where you have a circle. Really, you don't even need the circle, you just need the radius. So really, you just need a triangle, where you're in this situation where you have an angle and it touches a circle, or it just creates a triangle, and it touches at x comma y. Okay, but then what people do was sometimes they just take away the fact that they're on the xy axis. So they say, like, forget the circles and forget the xy axis. What about just the triangle? So they say, forget the whole thing, just give me a triangle. And then if I think of things instead of x, y, and r, if I think of them in terms of like relationship to this angle, and I think of this as like, this is like the opposite side to that angle. This is the hypotenuse. It's the longest side. And then this is adjacent to the angle. If I think in relative terms like this, then I could just say the same thing a little bit differently. I can say sine is y over r, but that's really just the opposite side over the hypotenuse. And cosine is really just the adjacent side over the hypotenuse. So this is where you'll hear people say something like SOHCAHTOA to remember these relationships. We haven't talked about TOA yet, so I guess I'll cross that out. SOHCA. So what people do is they use this if there is no XY coordinate going on, there's no circle going on, and they use this if they're talking about a circle of radius r. Okay, so this is a whole bunch of sort of theory building. Now let's get into some sort of problems that you might be expected to do. Okay, this is a little bit more grounded. So one thing you could do is say something like this. If you know that sine of an angle is 4 over 5, you can find cosine of that angle. Where you don't know anything about the angle necessarily. So how can I possibly do that? Well, what I'm going to do is I'm going to use sine's relationship to the side lengths of a triangle to draw a triangle, specifically a right triangle. So what we know is that sine of theta is 4/5, but we also know that that is the same as the ratio of the opposite side to the hypotenuse side on a triangle, as long as you draw the angle appropriately. So if you just draw your triangle and you pick one of these to be theta, you can then label the opposite side as 4 and the hypotenuse side as 5. And then you can use the Pythagorean theorem to find the adjacent side. So maybe I'll call it A for adjacent, just as a hint. So what does the Pythagorean theorem say? It says that if you add the square of the sides, the shorter side, so you add a squared plus 4 squared, that should equal the hypotenuse squared. So I can calculate this pretty quickly, 16, 25, then I subtract it over. That gives me 9, square root that, and I get 3. So A is 3. So what does that mean about the question I'm initially trying to figure out? I'm trying to figure this thing out. Well, what is cosine on a triangle? Cosine on a triangle is the adjacent side over the hypotenuse side. So in this situation, it's 3/5. Okay, so that's it for that problem. There's lots of very similar types of problems. So let's do one more like that. So if, how about this? Cosine is 5/13, find sine of that angle. Same idea. I already know cosine is the adjacent side of a triangle divided by the hypotenuse of the triangle, as long as I draw the angle first and then label afterwards, I won't get mixed up. So I make a triangle, pick something to be theta. You could pick this one to be theta instead. It actually doesn't matter as long as you draw accordingly afterwards. But I'd like to stick to this one, so I always draw it down here. So I'm going to label, so that automatically means that this is my adjacent side and that this is my opposite side and this is my hypotenuse. The hypotenuse won't matter where you label, but the other two will. Okay, so I know my adjacent needs to be 5 and my hypotenuse needs to be 13. And my opposite side, I guess I'll call that B for opposite or something, because O looks too much like 0, so I'm not going to use O for opposite. So B for opposite, and then I can say that 5 squared plus B squared equals 13 squared. From this triangle, Pythagorean theorem again. So 25 plus B squared equals 13 squared. Oh, what can I do in my head? Yes, I'm a genius. 169. Definitely did not look that up ahead of time. And then if I just subtract 169 minus 25, obviously 144, again, using my genius subtraction skills. I did not look that up ahead of time. I get 144. Square root of 144 is 12. So that gets me 12 to be that opposite side length. So then to figure out what sine of theta is, I just need to do the opposite side over the hypotenuse. So that's going to be 12/13. Okay, so that's how you work these triangles that are just sort of floating in space. But what about back in the XY plane? Back in the XY plane, you can still think in terms of opposites and adjacents and hypotenuses, but you can also think about it in terms of X, Y, and R. So you might get examples like this. Cosine of theta is 1/7. but they have to tell you something else. They have to tell you where theta is. So they might say it's in quadrant 4 or something. Then you can find sine theta. Because now we're not just looking at a triangle. We can't just draw a triangle wherever we want. We have to consider positives and negatives because we're on the xy axis. That means we need to know where theta is. Okay, but other than that, it's mostly the same, meaning you use this to draw something. And this is telling you where to draw it, okay? So first, draw theta in quadrant 4. So we don't know what theta is. We don't know the angle. We just know about the angle. But we do know it's in quadrant 4. So remember, it was 1, 2, 3, 4. So we know it's over here somewhere. So just draw however you want. So that's going to be our theta. And then, what do we know? Now we know this. Cosine of that angle is 1/7. So cosine, when you're on the xy plane, is the ratio between the value of x that you go over divided by the divided by the radius of the length that you go down. So, or you go from the middle to the end. So that is going to be a 7. Oops, x over r. So that means that we can draw a picture like this, and you can think about it in several different ways. So then you can think about it as, if I draw this triangle, this length is 1, because the x coordinate is 1, and the y coordinate is what I don't know. And because it's going down, it's going to be negative. It's got to be negative. And so you can think about it also as like, oh, this line of length 7 touches the point 1, y, and I don't know what y is yet. But you can also think about it in terms of triangles. Okay, so how can I figure out this y coordinate, this y value? How can I do that? I have to still use the Pythagorean theorem again. So then use Pythagorean theorem. So how can I use it here? Well, now my hypotenuse is the 7, and my other side lengths are 1 squared. Sorry, my side length is 1, so I do 1 squared plus the other side length is y, and then I square it. I don't know what it is yet. And then 7 squared. So you get y squared equals, let's see, 49 over there, 1 here. So this time it's not going to be such a nice number. It doesn't always have to be like it was before. Then I square root both sides. And this time, because I know it's going down, I know that the square root needs to be the -1. So that is my y coordinate. So then how do I finish the question? Well, I'm not looking just for that y coordinate. I'm looking for what the sine value is at that angle. And it's not just the y coordinate, because I'm not on the unit circle, because the circle is radius 7. So in fact, it's the y coordinate divided by the radius. Okay, so that's the answer there. Just to relate it back to the unit circle, this is saying that if you did have a radius 1 circle with that same angle, then the y coordinate would be this. Okay, just a little bonus fact. Okay, because the y coordinate on the unit circle is the sine of the angle. That's the definition. All right, so let's do one more. So how about this one? If sine of theta is 3/8 and theta is in Q2, quadrant 2, find cosine theta. So again, same exact steps, but we can do it a little faster now. First step, draw theta in quadrant 2, draw it just however you want, and then label the triangle that it creates using the thing that's given to you. So here I know that the y is 3, and I know the radius is 8. Because sine of theta is y over r, aka I know that this point is something, comma 3. I don't know what that x is yet. But because it's going to the left, it's got to be negative. So there's my theta. So then I just have to figure out the x value by doing the Pythagorean theorem. So x squared plus 3 squared equals 8 squared. X squared equals 64 minus 9. What the heck is that? 50 something, 55. X squared is 55. And then you square root. And that's the x value, but it's got to be negative because I'm going to the left. So then cosine of that angle is the x coordinate divided by the radius. So there you go. So next, we look at other trig functions. So the thing is that if you have a triangle with 3 sides, you get many more ratios. So we can think about it like this, or we can think about it as opposite and adjacent and hypotenuse. But in any case, what's going on is that sine is just one of the possible ratios. So you can do your y divided by your r, your opposite to your hypotenuse. You can do your adjacent to your hypotenuse, which is x over r. But there's many other ratios, and so what we do is we define names for these other ratios too. So what else can I do? I could do my y divided by my x, and then I can flip all these 3 over. So I could do my r over my y, I can do my r over my x, and then I could do my x over my y. And so people often get these names all mixed up, but we'll try our best. So the first one I know for sure is called tangent of theta. So this is called tangent of theta. Then y over r, which one is that? That one is, I have to remember. That one is cosecant. So you might think it should be called something else when you'll see afterwards, but it's called cosecant, and it's written CSC of theta. Cosecant. And then cosine flipped over, you might think like that should be cosecant because they both start with the word co, but you're wrong. Unfortunately, that one is called secant of theta. So secant is the same as cosine flipped over. And sine is the same as cosecant flipped over. Tan and its flipped over version make perfect sense. They have the perfect name to go with each other. Tangent flipped over is called cotangent. So in a logical world, sine flipped over would be called cosine, just like tangent flipped over is called cotangent. But nope, that's not how it is. Okay, so these are the 6 ratios that you can get out of a triangle with 3 sides. And then you can do all the same stuff we just did with these ratios instead, but it doesn't change, the problems don't change, they're not any different. So for example, we could do the same types of problems we did before. Say like this time find tangent of theta if you know, I don't know, you know secant of theta is something, I don't know, like 7 over 5, and theta is in quadrant 1 or something like that. You can do the exact same types of problems, you just have to label differently. So let's go ahead and do this one. So how do I do this one? Well, I know that theta is in quadrant 1, so I draw my theta there. quadrant 1. And then secant, I'm not as familiar with, so I'll just cheat and look up here real quick. It's r over x. So this time, that means I'll put the 7 on the radius. And when I draw this triangle, my x will be 5, and my y is what I don't know. And I know it's going to be positive. But then I still use the Pythagorean theorem, same way I did before, to fill in the triangle. It's all about basically filling out the triangle using the pieces of the triangle that you do know. So now we get something like this. So 49 minus 25, what the heck is that? That's going to be y squared, 24. So y is the square root of 24. And then I look and I see which one am I trying to figure out. I'm trying to figure out tangent. And I know that tangent, that one I know better. I can write it down, y over x, without looking it up. So now I just use the information I figured out. So square root of 24 is the y, and 5 is the x, and then that's it. So there's many more problems like this. And the other types of problems are to fill out sine, just like we did sine and cosine of good angles, we also do tangent, cosecant, secant, cotangent of those same nice angles. But because they all just come from the y and the x, if you're on the unit circle, which is what you use to make these, to figure out sine and cosine of the nice angles. So because of all that, you can just use your answers to sine and cosine. That's the fast way. So for example, if I want to know what's a nice angle, how about tangent of, let's do like 5 pi over 4. That's one of those nice angles. So yes, tangent is y over x. But if I'm on the unit circle, which is what I should do to make things easier to calculate for me since I know more about the unit circle. Oh, sorry, that's not where 5 pi over 4 is. 5 pi over 4 is down here. Now we're pros at counting it out. So this is 5 pi over 4. So because I know that the point over there corresponds to the point over here, which is root 2 over 2 comma root 2 over 2, except I'm on the left now. So because I know that, then so the x and y are negative, all I have to do is use those two coordinates still to figure out tangent. So that tells me that tangent of 5 pi over 4 is the y over the x. Well, that's just something divided by itself. So actually that's a nice easy one that just cancels, even the negatives cancel. So I just get 1. So when you see like tangent of 5 pi over 4, or you see like cosecant of 5 pi over 4, or these other ones, it's not like a brand new problem. You just think of them in terms of x's and y's, and the r is just 1 in on the unit circle, and then you just use what we did before. Okay, so I'll do one more for extra practice. So find, how about the secant of, let's do 7 pi over 6. Okay, so first I got to know where 7 pi over 6 is. Well, here's pi over 6, and I'm pretty good at this already, so I already know that 7 pi over 6 is this one. And I remember the point associated to pi over 6 is root 3 over 2 comma a half, so then I automatically know that this point is the same except to the left and down. And then secant I might not know right away, so I'll cheat. I'll go up here again and I'll say, okay, secant was which one? Where did I put it? Way over here. Secant was r over x. But now I'm on the unit circle, so r is really just going to be 1 over x, luckily. But if I really think about it, x is actually just cosine of that angle. Whoops, 6. So the trick is actually it's just cosine on the bottom. So as long as I already know what cosine was, all I have to do is flip it over. So cosine is the x value. And so what I'm really doing is I'm just flipping over cosine to get secant. And that is how they are related. Secant is just cosine flipped over because I'm flipping r over x into x over r. And sine is just cosecant flipped over for the same reason. So that's another way to do it, which is to notice this. Sine of theta, that's just 1 over secant. They're flipped over versions of each other. Oh, sorry, that's cosine, not sine. Yeah, see, I always get these names mixed up. And then sine is the other one flipped over. So you can use this fact a lot. You can flip over your previous answers if you want to know, like, what the heck is cosecant of pi over 3, just flip over sine of pi over 3. And then that one you might remember more easily. I always have to like redraw it. So here's pi over 3. You go over a half, you go up root 3 over 2. Looking at sine, I'm looking at the y value. So I'm really just flipping over the y value. And then that's it. Some people like to do rationalizing, which means they simplify it a little bit by multiplying by root 3 over root 3. And then they cancel like that. So that's acceptable too. I could have done that over here as well. So then I would have got this instead. Okay, so that's enough for today. It's a pretty long lecture, I think. All right, see you next time.